What's going on, modern people? This week's lab, I should really stop saying this week's lab. It's just kind of built in. You could be doing another lab this week. This week's lab is photoelectric effect. Um, the lab itself is so easy that I will definitely just be putting it into the end of this video, the instructional part where I'm with the equipment showing you how to do it because it's incredibly, I'm going to call it like plug and play. Um, there's just one wire. It's the power cord. Everything is just dials on the machine, so it's very self-contained. So the data taking, the analysis, all of that will take you half an hour tops. Like I'm saying tops. So I thought it would be a good idea just to kind of get a refresher on what the heck the photoelectric effect is, why it's so important, and the history behind where all this happened. Because this is really where modern physics started at the turn of the century, when Einstein and Planck were doing a lot of these things. So let's get started, just slowly going through some of these things. So what did Planck start with? Planck's postulate was that energy is quantized, i.e., if the system is oscillating, then it's oscillating with some frequency, and that energy is correspondent to that frequency. In other words, I can only take on discrete values. That's another way to say, quantum, 1, 2, 3, 4, classical 1.1245. It's this discrete versus continuous. So this is the equation for it, but this is not super useful for us at the moment. Let's just kind of delve into why. Like before we explain how Planck and Einstein used this, let's say, why did Planck even do this? It turns out his objective was resolving something. It was both of these, Planck and Einstein, were supplied with experimental anomalies. We'll talk about the photoelectric effect in Einstein in a second, but Planck was trying to figure out how to explain black body radiation. And it turns out it had been perplexing people for, a decade plus, this UV catastrophe, as they called it. And it arose because of thinking about what was going on in purely classical contexts. So let's just start talking about what a black body is. This is actually I'm going to be referring to your modern physics textbook for this one. So I've actually put the excerpt that I'm talking about down attached to this PDF as well. So let's look at this figure 3.8. This is chapter 3 in your book. 3.8. Here is a black body somewhere. There it is. So light goes in and can't escape. So just in words, what is the black body looking, what is it doing? The black body is effectively something that absorbs all incident normal, E&M radiation like light, um, and it does not emit any light. Rather, it heats up and then emits thermal radiation. So it's just a different type of electromagnetic radiation. I'm using the word quotations here because technically, like this canonical cavity picture of a black body where you shine light in, it can't escape, and it heats up, there's technically still a hole in it. So it absorbs almost all of the incident light and it emits almost none light, but technically there could be. So the idea here is that as the black body heats up, it will glow with different colors. So this is effectively how blacksmiths, I have way too many tabs open here. We don't need any of this anymore. I covered that in the other video. This is effectively how blacksmiths, in old times, but there are still blacksmiths around today, how they determine whether their material is ready or not, based on the color of the glow, just based on, anecdotal evidence of their apprenticeship and things like that. When the glow is the right hue, they know it's the right temperature. And so the reason for this is because the intensity of the thermal radiation, it peaks at different wavelengths, and those wavelengths correspond to different colors. So in the textbook, we've got this figure here, 3.9, which shows us that the intensity, the amount of radiation that's coming out, the intensity peaks at different wavelengths. So those different wavelengths are going to correspond to different colors. And so this also has, a huge application in terms of astronomy. Because if you can figure out, you know, just looking at the light, taking in data, getting data about the wavelength that the light emits, you can actually determine the temperature of the star that you're working with. So incredibly useful on the astro side as well. Okay. Okay, so here's where the UV catastrophe arises. If we imagine that as this black body heats up, if we think about the wall, like that cavity, the light goes in and kind of bounces around. If we think about the wall, the thing that's absorbing that energy, as just a bunch of oscillators, like masses and springs, the kind of bed spring model of matter, then as it absorbs all the different types of light, right? Light is just complete. There's all different types of wavelengths in white light. Then all different types of motion will occur, all different types of oscillation. You can have translation, you can have vibration, rotation. All these different things can occur at different frequencies and with different amplitudes. So before we go on a little bit, just a little bit of a warning here. There's a little bit of weird math stuff coming up, some buzzwords that aren't super useful for understanding the photoelectric effect. I'm just kind of explaining how Planck got this. Because to me, the idea, I've always been fascinated about that, how the people around the turn of the century went from a classical mindset um, to a quantum mechanical mindset. And it turns out that Planck actually made this postulate by accident. What do I mean by that? The UV catastrophe basically occurred because when you're working with classical thermodynamics or statistical mechanics, and again, that's a subject of another course later on in the sequence that you'll be taking, there is some mention of these topics in chapter 9 of the physics textbook. I didn't include that one there because it's goes too much into the weeds, but basically, there is something in classical or thermo or stat mech that is called the equipartition theorem. And it tells us that all the different possible states of a system, in our case, the modes of oscillation that we were just talking about with the matter on the wall, are equally likely, even ones with ridiculously high frequencies. So Planck discovered by accident that if he used this equation that he postulated, then the distribution function, again, the distribution function, not a huge thing to realize. It's basically how likely it is for things to be at different states. The distribution function matched the UV region of the experimental data. I'll talk a little bit more about this UV in a minute. There's a reason why it's called the UV catastrophe as opposed to the IR catastrophe. So one I'm just gonna, make some notes here. The idea of going from an energy equation or a function for the energy to a distribution function is very in depth. It involves the partition function and lots of different things that we don't really need to discuss here. But what does by accident mean? Effectively, Planck was doing a little math trick that you'll learn in something like 520 or 5200, 5200. He was going to eventually let this undetermined constant, he didn't call it Planck's constant. It was just a dummy variable that he was going to be using. He was eventually going to take the limit where that goes to zero. And so if that's true, then technically all the infinite possible energy states would be accounted for, but if H goes to zero, then the energy could effectively have a arbitrarily low value, which would effectively nullify this. And that's why this is like a math trick, because technically this means your energy levels are quantized. And at that point in history, people weren't doing that. That wasn't a thing that people did. So he would have gotten rid of his quantization by letting this limit occur. However, he discovered that this actually matched exactly what was happening experimentally. So effectively, this just, that's kind of a lot of jibber jabber for the moment. He discovered that by leaving the energy quantized, all these possible energy states were no longer equally likely. So we kind of broke the partition theorem. You get into the quantum equipartition theorem a little bit later. So effectively, the infinite contributions that came from the infinitely high frequencies that you could have, you're just going to get more and more contributions. And this is, high frequency, low wavelength. That's kind of the UV region. That's why it's called the UV index. They just weren't causing disagreement with the experiment anymore because they weren't as equally likely. So that's what Planck did. And then very, very soon after, Einstein took this a step further to not only say that those molecules that make up the black body itself are oscillating, but light is also oscillating, and it has this kind of quantized energy level. So he was thinking that the quanta of these light energy, this using the exact same thing instead of the modes with the n quantized, he was saying that an energy or one photon, and he was thinking about this in terms of particles because his motivation for this was to try to explain something called the photoelectric effect from a collision perspective. Basically, he wanted to think about photons coming in and hitting electrons and kind of knocking them out of their, obviously it's not quite a billiard ball situation when you're working with things like that. They carry the energy. But this is going to give us a little bit easier picture, especially because of the weird thing that was happening with the photoelectric effect. So figure 3.11 in our textbook is, or in your textbook from previous, um, is basically the kind of experimental setup for the photoelectric effect. You've got a power supply, you've got a sheet of metal. If you apply some voltage to this, eventually um, the incident light that comes out of this emitter will, where am I? Oh, incident light. This is an awful figure. I'm gonna go back to. I've got a bet. I drew a better figure myself. There it is. Uh, okay. It's better to just do it in words. That figure is kind of crappy in my opinion. So effectively, when light is shined on a metal plate, the valence electrons in that metal plate will absorb the energy from that light. And if the energy is enough to ionize those electrons, break their valence bonds, then the emitted electrons will come off the metal and they can be collected and measured as a current. So that's effectively what the photoelectric effect is showing. But something weird happened. The weird thing that happened was if you shine brighter and brighter light on the metal, nothing changes. What does make, and by nothing changes, I mean you don't see any increase or decrease in the current of the emitted electrons. However, if you change the frequency of light, i.e., the color, if you shine red light versus blue light on the metal, that will be different, or that will cause a different current. So this is weird, because if we think about, previous to Einstein thinking about light as particles, if you think about it as a wave and it has intensity, the intensity of the wave determined by the energy. And I think it's easiest just to have something to work with as we're discussing this. So let's just use simple harmonic motion. We know that we can just, talk about that in terms of waves. So let's just use that as our kind of example here. So energy 1/2 Ka squared, where K is the wave number, A is the amplitude. And the wave number, we know that's kind of related to the frequency as well. So it is dependent on the frequency, but it's dependent on the amplitude squared. So you would think that if you just shine brighter light, it will give more energy to the light in a better way, right? This has a linear dependence. This has quadratic dependence. So you would think that shining brighter light is more important than frequency, but it turns out it's not a or the situation. It's really just the frequency that changes things here. Okay, so Einstein thought that if the light didn't have high enough frequency, and by his and Planck's inspiration, picture not enough energy, then the photons that are colliding with the electrons wouldn't transfer enough energy to them to break the valence bonds. So more intensity would just lead to lower energy photons, photons which have smaller work functions, so that when you're breaking those work functions we'll talk about in a second, it's basically another word for the strength of the valence bond. Um, if you shine brighter light, you're just going to get more low energy electrons. If you change the frequency, more frequency would mean higher energy photons and more emitted. electrons because now you have higher energy, so you're emitting more electrons, you're overcoming different work functions, then you get more observed current. So let's summarize. Incident photon comes in with some energy. It hits a metal, which has some valence electrons. And yeah, this is what I was talking about. The bond strength, that valence bond strength, is determined by the work function. It's basically how much energy the electrons need to break their valence bonds. It's just another word for it, in my opinion. So if the photons have a frequency that's high enough, and thus the energy is high enough, then the incoming photon will overcome that work function, break that work function, and then whatever energy is left over will be kinetic energy of an electron shooting away. So in a picture, I think this picture is a little bit better for our purposes. We've got an incident photon coming in, so some light is being shined on a chunk of metal. This chunk of metal has some valence electrons with work functions. And if this energy is greater than that, the electrons will be emitted with some kinetic energy. In terms of an equation, it would look like this. Initial energy coming from the photon, that's Einstein's postulate or Planck's postulate as well. Planck's constant and the frequency, the work function in order to break the bond that they have with their nucleus, and or electron cloud, and the kinetic energy of that emitted electron. Okay, so now what we're going to do is once we start actually needing this figure here, the way the experiment runs is by applying a voltage. And if you apply a strong enough voltage, right, this is just connected to one end of the potential difference, another end of the potential difference, you can create an electric field in here. And so, because these are electrons, they're charged particles, they're going to interact with an electric field. If you apply a high enough voltage, where'd it go? Then if you apply a high enough voltage, you will stop the electrons because that voltage will lead to an electric field. And if they're emitted with some speed, they have a fixed energy. And so if you apply a high enough voltage, that energy will be effectively converted to potential energy, all that kinetic energy. So if we think about the relationship between voltage, so some potential difference, and potential energy, I'm just going to use the symbol U here, then for us specifically, what we're saying is that the kinetic energy, 1/2 mv squared, has been converted to the electron charge and the voltage across the plates. So now our equation looks a little bit different. We've got incoming photon energy, the work function, and if it has stopped, right? So if we apply a high enough voltage so that there is no observed current, then this is the potential energy that is stored now. And that is something we can measure because we are specifically applying the voltage ourselves. So now that we have some kind of situation here, what we're going to see is that if we shine a higher frequency on the metal, then the electrons are going to have higher kinetic energy. If we increase the initial energy, then the final energy is going to be bigger as well. So we would need to have a higher stopping potential. That's what the word for this in terms of the photoelectric effect experiment. You call this voltage the stopping potential because it's effectively stopping your electrons so that you don't measure them. So in our experiment, we are going to be shining different light on something. That's our independent variable. We're just going to shine red light, blue light, yellow light, all sorts of different colors lights. And then depending on what frequency we supply, we're going to need to change the voltage so that nothing is measured. So that means our independent variable is the frequency of the light. Our dependent variable is how much voltage we need to apply to the system to not observe any emitted photons. So at this point, now we know what the independent variable is and we know what the dependent variable is. So let's make this equation look more like a line. Let's linearize our equation. So we have this equation and it's a little bit, backwards. By linearize, I mean, we want it to look like the equation for a line. Y equals mx plus b, where x is independent, y is dependent. So let's rearrange this equation a little bit. My dependent variable is kind of over here. So I'm just going to rearrange a little bit, put EV on the left-hand side so that it matches with this. bring this HF inside, and then I've got my minus phi coming to the left-hand side. I'm just kind of reversing the order here. So cleaning things up a little bit, dividing through by the charge of the electron, I've got my dependent variable, my independent variable, my slope, and my intercept. So that means if we plot the stopping potential on the y-axis and we plot the frequency on the x-axis, our slope will be this quantity. And if we multiply that by the charge of an electron, we'll determine what this Planck's constant is, the thing that he just kind of thought wasn't important and was going to let it be zero eventually. And we can also, if we use the intercept, determine the work function. Um, the slope, we will need to do one bit of calculation there. We'll need to multiply it by the charge of an electron, but we actually don't need to do anything to this. Because if you think about the units of this equation, volts, volts, it turns out that most work functions are reported in electron volts. So electron volts means that if we have a number, let's say our number for the intercept is 2.7, because it's volts equals, that means that's 2.7 volts, and we can just rearrange. If our intercept is phi over E, then it just becomes 2.7 electron volts, not volts. So this electron volts is something that we'll be able to compare. And this is, I mentioned this a little bit later in the kind of instructional part of the video. That is something that we can actually test, right? You just Google what Planck's constant is, and you can tell whether or not you got there. But with the work function, you actually need to know what metal you're shining the light on. And that's something I actually have to reach out to the company for. So I'll talk about that a little bit in the procedural video, which is incredibly short. So I'll just tack it onto this video. All right, enjoy. Easy lab this week. All right, folks, hard part is done. This theory intro is the majority of this kind of intro video because it turns out the experimental instructions for this part of the lab, this lab this week, are incredibly easy. So let's just kind of jump through this whole original lab document. I would just refer to this one, quite frankly. Let's go all the way down here to this procedure. I've crossed out quite a bit because a lot of what we're doing is not involving the lasers. I thought it really did not offer anything. So start up for this. And what I meant by plug and play, this is the entire lab. There are no wires. There is one power cord that goes into an outlet, and then we've got this device that we're going to be working with. So incredibly easy to work with. I labeled this draw tube because it does mention the word draw tube in these instructions, but effectively these instructions are pretty easy to understand. Let me just focus on some of these things that are a little bit tricky. One of these, our first objective is positioning the light source 25 centimeters away from the draw tube. This is incredibly poorly designed. It does not, tightening or loosening this does not really help in any way, shape, or form. So if you can just get it to something around, just as long as it stays at the same location throughout the entire lab, you can see it kind of, there we go, kind of stuck there. That's totally fine for me throughout the entire lab. I want display mode in current at the beginning. That's over here, display mode right there. My current multiplier I want at x1. Light intensity, I want this all the way down at first. This one does click. This one does not click, but it does have this lower limit, so I want it to be all the way down. So then I'm going to have my voltage in the minus position. This isn't really super important, it's minus versus plus. Next thing I'm going to do, all this crossed off stuff is all part B of the lab, which we are not doing. There's really no reason to use lasers because we have these colored filters, which we'll get to in a second. So first thing we're going to do is we are going to insert one of these filters after we power it up. So let's power it up. We're just going to turn on, and then we're going to slowly start ramping up our light intensity, and then this light will start shining. There we go. Okay, So what we're going to do is we are going to put in one of these one of these colored filters. So let's put the red one in first, and notice it has the wavelength on there. We do not want wavelength, we want frequency. So you're going to need to use the speed of light and invert this to get your frequencies. Remember, that's going to be your independent variable. Now, how do we get our dependent variable? Our dependent variable is the amount of voltage we need to supply to this device to get the current to stop. So what we're going to do here, we're going to set the current multiplier to a much lower number, and you'll see that as soon as we do this, it is actually measuring something. So those are the electrons being emitted, because inside this draw tube, and I'll talk a little bit more about this because I've actually taken this apart and looked inside it, is the sheet of metal that the electrons are being emitted from. So light is shining in, hitting a chunk of metal in there, and then being detected. So what we're doing, this is how we're going to get our dependent variable, right? We've assigned the independent variable. We're going to adjust this knob until, remember, what is our whole objective here? We are trying to get this equation to work, and that value, our dependent variable, is when the kinetic energy has been transformed to potential energy. So that means the electrons have stopped. They are not moving anymore. So what we're going to do is we're going to increase this until that number gets to 0. Almost. And a little bit more. And there we go. So now that we're not seeing any current, we need to know what the voltage is that makes that happen. And so that is the dependent variable that we're going to keep track of, 0.23 volts. So convert that to frequency. That will be our independent variable, and then this will be our dependent variable. And then we just do the exact same thing for all these different colors. So same thing again, we're going to go back down on voltage, bring this to 0.1, put another color in, and do the exact same procedure. So that's pretty much the entirety of lab. And you'll notice, I don't see any uncertainty in anything here. There's no uncertainty listed in these wavelengths and thus frequencies. There are no uncertainties labeled here. So there's quite literally no error analysis to do for the entire lab. So it is an incredibly self-contained lab. The theory intro, you watching that video, is probably the most work you're going to be doing for this lab. So remember this, where I said I unscrewed this and looked inside it? The reason I did that was because remember what we can get information about. If we plot this on the y-axis and this on the x-axis, if we multiply our slope by the charge of an electron, we'll get Planck's constant. This one, a little bit easier, you can just kind of read it off like it mentions in the theory intro, but the intercept should be the work function. So that's also something that we'll be able, once we plot those two things, we should be able to read this off as well. Planck's constant is something that we can just Google and make sure that we did it correctly, but this is not. It depends on what type of metal is inside that device. So I unscrewed it, looked at everything. I could not find any labels on the device, but thankfully I went and found this device. Ooh, it's on sale, only $800. And I still couldn't find it. I went to the manual, nothing. There was no information about what type of metal was in there. But thankfully, I reached out to the company and they let me know that this is the work function that we're expecting. Something in those, it's cesium, I forget what that one is. We're looking for this work function. So we're trying to confirm Planck's constant, and we're trying to confirm that that is the metal inside this device. All right, have fun, y'all. Easy lab this week.